Thank you for listening to this talk, Evaluating the Needs and Sustainability Barriers of Commercial Strawberry Growers in the United States, a Mixed Data Clustering Approach. My name is Megan Donovan, and I'm from the University of Florida. The United States leads the world for strawberry yield and value, with 1.6 billion pounds of strawberries produced in 2017, with an estimated $3.5 billion in value. Fresh strawberries, either domestic or imported, are available year-round, with peak volumes occurring from February through June. The United States imports berries during the off-season. Importing rose substantially in recent years, alongside an increase in consumption and a decrease in strawberry acreage. The purpose of the present study is to identify and evaluate the needs and barriers to sustainability of strawberry growers in the U.S. who do not market through the major supply chains, to inform future development of the strawberry industry in the U.S. A national needs assessment survey of strawberry producers was conducted in 2016. The questions asked about the producers' demographic characteristics, the farm attributes, and questions on limitations and barriers to success and sustainability in production. The final sample was 105 U.S. strawberry producers. The respondents were primarily from 30 states outside of California and Florida. We performed mixed data cluster analysis to identify salient groups or clusters of commercial strawberry producers in the United States. The analysis was conducted using R. Homogeneous clusters were formed based on a set of the producer's demographic characteristics, the farm attributes, and limitations and barriers to success and sustainability in production. We first estimated the Gowers distance coefficient. Then we used partitioning around meadoids, or PAM, to identify salient clusters of producers based on key limitations in strawberry production. Finally, the average silhouette width was utilized to determine the clustering quality. Table 1 shows the results of the sample farm characteristics. A little more than half the farms were relatively small acreage, 50 acres or less. More than half the farm acreage in strawberries was 2 acres or less. Strawberry production was a secondary source of income for a little over half of the sample. Most of the sample used a plasticulture-only production system. Most farms in the sample used conventional practices, and more than half the type of the strawberry planted was short or day or June bearing. The continuation of Table 1 shows the descriptive statistics for the sample's demographic characteristics. The sample contained mostly white men from the South. A little more than half of the farmers have a bachelor's degree, and almost half were members of a growers association. Gowers distance coefficient was estimated based on the Kaufman and Russo extension. That is the average of partial dissimilarities across farmers, where each partial dissimilarity ranges from 0 to 1. The dissimilarity between two strawberry producers, I and J, is represented by equation 1. Equations 2 and 3 show the estimation of partial dissimilarities for the different possible levels of measurement of the variable K. Equation 2 is when K is binary or nominal, and equation 3 is when K is continuous or ordinal. In partition clustering, K clusters are formed from a data set. Each cluster contains one individual, and each individual must belong to only one group. The two partitioning techniques of clustering are K-means and K-meadoids. K-means use mean values to arrive at K clusters, where an individual belongs to a cluster with the nearest possible mean. K-meadoids use meadoids instead of means to form K clusters. Meadoids are data points designed as the center of the cluster. The meadoid represents a set of individuals whose average dissimilarity to the rest of the individuals in the data set is the smallest. The K-meadoid clustering technique uses meadoids to form K clusters that minimize the sum of the dissimilarities of all the objects to their nearest meadoid. In our study, we use k-meadoid clustering because it is less sensitive to outliers and noise. Equation 4 shows how the meadoids are calculated. Partitioning around meadoids, or PAM, was the meadoid-based algorithm used in the study. In the first stage, PAM chooses the data item with the smallest Gowers distance to other individuals in the dataset. The Gowers distance, again, is the average of the partial dissimilarities across all the strawberry producers. This is repeated, and the next items with the smallest distance to the other data points are added to the selected objects, or O. The remaining unselected items, or U, are placed around their closest meadoid. The next stage, called swap, tries to improve the quality of the clustering by analyzing the effects of replacing a meadoid for a non-meadoid. The total swapping cost can be calculated as shown in equation 5. This swapping cycle is repeated until there is no effective replacement of meadoids, signaling there is no further improvement needed. Again, we get another set of O and U. The average silhouette width over different cluster scenarios can tell us about the quality and the appropriateness of the clustering. We can be informed about the number of clusters to adopt and which strawberry producers are in what clusters. The silhouette width is calculated using equation 6. The mean of SI for all the farmers in the dataset is known as S bar K, or the average silhouette width for the entire dataset. We used S bar K in this study to decide the number of clusters, or K, and the quality of the clustering. Table 2 shows a detailed description of each farm characteristic variable. The variables are on the left, and to the right, you can see the levels of measurement and the response options. The continuation of Table 2 shows the detailed description of each farmer demographic variable. Again, the variables are on the left, and to the right, you can see the levels of measurement and the response options. This part of Table 2 shows the description of the variables measuring barriers to, needs, and sources of information for sustainable strawberry production. Farmers were asked about the barriers to managing their strawberry production systems. They were also asked about their information and technology needs regarding sustainable strawberry production. Farmers also reported where they received their information about managing strawberry production systems. 5 distinct clusters emerged from the analysis. Figure 1 shows the silhouette width. This figure shows that 5 clusters maximizes the meaning of the analysis. The farm size mentioned in the clusters refers to the acreage of the farms. Please refer to Table 3 in the handout for the complete profile of each cluster. Shown here are the characteristics of Cluster 1, the experienced older growers. These are very experienced, highly educated, older, and predominantly white men. They belong to a growers association, generally operate medium-sized farms, and the only group that predominantly uses matted row in integrated pest management. This cluster was split among strawberries being the primary or secondary source of income. This was the only group with a true 50-50 split, but cluster 4 was 40-60. This cluster names pest management as their biggest barrier. They named remote sensing as their main technology need, and also named alternative production systems. This cluster primarily gets their information from formal and technical training. Cluster 2 is characterized by middle-aged white men. These are experienced growers operating medium-sized farms. They have less formal education, and the only group that strawberry production is the primary source of income. They belong to growers associations and use short day only strawberries. This cluster names climate variability as their #1 production barrier, with pest management coming in at a close second. This cluster names alternative production systems as a need and computer and mobile applications. Primarily, this cluster gets their information online. Cluster 3 makes up young, middle-aged, mostly white, and well-educated women. This cluster has limited experience producing strawberries, They're not part of growers' associations, and they operate small acreage organic farms using plasticulture with short-day berries. This cluster named climate variability as a production barrier. This was the only group that did not name technology as a need. This cluster gets their information from peers and service providers. Cluster 4 is made up of mostly middle-aged, non-white men with less formal education. They are operating small acreage organic farms with limited experience growing strawberries. Strawberries are the secondary source of income and the only cluster using day-neutral strawberries. This cluster wants technology such as mobile applications. They named financial and risk management information as a barrier. They largely get their information online. This cluster is made up of mostly middle-aged white men with college degrees. They are members of growers' associations and experience growing strawberries. They operate large farms using plasticulture and short-day strawberries. Strawberries are a secondary source of income for this cluster. These farmers name financial and risk management information as a barrier. They are the only group that were interested in predictive models. They mostly get their information from formal training sources. Figure 2 shows the visualizations of the clusters. As you can see, clusters 3 and 4 are close together. This makes sense because they are similar characteristically. For example, they both operate organic systems. Other clusters are more dispersed, like cluster 1, for example. In conclusion, the interests and barriers of this sample of growers are different than those of major market chain growers. This makes sense because the instrument was not aimed at the large-scale commercial growers in the primary production regions, California and Florida. These large-scale growers already have huge research and extension support serving their needs. The growers in this study have different needs, even within the sample. One research program would not be sufficient to address the needs of this group, particularly because experience was varied among the sample. Most clusters identified the need for different technologies such as mobile apps, remote sensing, and predictive models. More research funding should support organic and other alternative production systems. Clusters 3 and 4 especially demonstrate this need. The small sample size was a limitation in this study. This was a targeted sample of growers, not easy to find. There was no data in the sample for farm revenue. Strawberry production revenue, specific local or regional chains where producers market their berries, like direct sales to restaurants or specialty grocers, land tenure, and diversity within the non-white group. For further research, an evaluation of the current resources available on organic and alternative production systems should be done. Are these resources effective, educational, reliable, meeting the needs of growers? Also, where and how these producers are marketing their strawberries likely could be its own survey. This would help establish a baseline as to how much this non-major supply chain of strawberry production is adding to the economy. Here are our references. And please reach out to myself or Jorge if you have any questions. Thank you very much.